So thank you for joining the room back. We are starting a few minutes ahead of schedule to be sure we finish on time. So if you allow me, my name is Grégory Liev. Good afternoon, everyone. If you allow me, I will take a few minutes to share with you the drivers which led us to define that agenda. So yesterday was really dedicated to technical topics. We spoke about cert memos, we spoke about how to certify a PED, where we were on SMS. So the first day was really about practicalities. The second day, we wanted to split the day into two parts. So in the morning, it was really about us working with you and the interaction. For this afternoon session, the idea is to take a bit of a different perspective. Last year, if you recall, we spoke about sustainability. And as was mentioned a few times yesterday and today, we see really two big challenges coming our way, which will really introduce deep mutations of our business. One is the sustainable challenge, the other one is digitalization. So the purpose of this afternoon session is really to look a bit further and to reflect about the state of play of digitalization. So that's a very wide topic. When we built the agenda, we had tons of ideas, and we had to focus a little bit. So it's really digitalization in the way it impacts how aircraft are certified. And for that, we have two sessions. So a first session, which really will be dedicated to the outside world, what's happening there. And I'm looking forward to hearing some fascinating presentations from the panelists who will join us in a minute. And then we'll end up with a session when we merge everything, like digitalization in EASA, digitalization outside, and how we work together and make this happen, as Florian said this morning. So I would now invite the panelists to join me on stage. So we have 4 panelists for this first session, and we'll divide the first session into two portions. The first one is really about enablers and transversal topics pertaining to digitalization. So we have Mr. Christophe Risse from the DLR, who will tell us more about simulation, how far, how fast, what can be reasonably expected, how can we look forward. And then we have Mr. Philippe Leclerc from Thales, who will talk about a major enabler, which is securing data, security, and please take your seats. And how this is critical if we want to make digitalization a reality. Then we'll take a series of questions, and we'll continue with 2 more focused presentations, the purpose of which is really to show you what is happening today, to make sure that digitalization is more than a buzzword, but a reality. And you will see that in industry, some are very advanced. So we'll hear Francesca Barrosio from Leonardo Helicopters about condition-based maintenance, a very practical effect of digitalization. And then we have Mr. Yao Chujin. I rehearsed on the way to pronounce your name, Mr. Yao, I'm doing my best, from COMAC, who will present a project about a full digital process in COMAC. So a very stimulating list of speaking points, and we start with Christophe. The floor is yours.
So thank you, Grégory, for the kind introduction. Good afternoon also from my side to all participants here in Cologne as well as online. And again, thanks first to the EASA for the invitation and the opportunity to speak here at your conference. So my name is Christoph Risse from the DLR German Aerospace Center, working at the Program Directorate Aeronautics and also leading the Virtual Product House in Bremen. So, and in my talk today, I would like to give you an overview about virtual and physical testing, our DLR perspective, and on how modeling and simulation can help us to accelerate the certification process or even the whole development of new aircraft technologies and components. And I will start my presentation with our general DLR view, according to the session title on digitalization in aviation. Then I will focus on the challenges and objectives of virtual testing and certification. And afterwards, in the end, I will give 3 selected DLR examples. And here I also want to thank really valuable contributions from several DLR colleagues and institutes that are all working on this broad topic. So if we start with a, let's say, general view on digitalization and aviation, we can say that the common objectives in aviation are to make it climate compatible and sustainable, for example, by more energy efficient aircraft configurations, propulsion operation concepts. And at the same time, of course, we want to develop new products in even shorter lead times, also new technologies, and at the same time want to keep the same quality and safety standards, which are really high, so the safety requirements. And here, for these conflicting requirements, the digitalization is one or the key enabler or accelerator. And to illustrate this a bit, I brought our DLR virtual product digitalization video, which shows, let's say, the potentials and benefits of digitalization along the life cycle. And maybe you can see it in the background. I can go through it and explain a bit. So first, in the design phase, in the aircraft design phase, digitalization or simulation helps us to faster explore the aircraft parameter design space. And this parameter space also has grown because of new configurations and propulsion concepts. Then we can also accelerate the whole development process if we digitally connect end-to-end the phases. That means from design, manufacturing, up to testing and certification. And later in the life cycle, we can also apply digital twins, for example, or AI methods to series production or to operations, for example, for prescriptive maintenance or climate-optimized routing and operations. So in the end, we want to exploit all these digitalization methods, but on the other hand, we also have to regulate them, as for example proposed by the EASA and their AI roadmaps. So from the DLR side, so German Aerospace Center, how is this covered in our aeronautics program strategy? Actually within 4 pillars. So the first pillar is the energy efficient aircraft, covering mainly the airframe. So energy efficiency by new configurations, components, but also improved aerodynamic structures, materials, and systems. Then the low emission propulsion, both for improved conventional engines like UHBR and open rotor concepts, but also completely new propulsion or energy concepts like for example, SAF, hydrogen or hybrid electric or batteries and fuel cells. And then the emission-reduced air transport system, including atmospheric research, climate impact, or also improved ATM concepts. And then the 4th pillar is the digitalization, really cross-sectionally enabling the other pillars, as described before. So the focus today on virtual testing and certification, or certification by analysis, concerning the timeline, because this was in the title, how long or how far, how fast. We can say, on the one hand, we have really short-term projects and milestones up to the end of the decade and running projects to certify specific components virtually. But we also see this topic of virtual certification really as a long-term vision and long-term goal together with our partners, so up to 2040, 50 and beyond. So what is now the benefit and the objective of virtual testing and certification, and also the challenges? First, the idea behind virtual certification is really to apply modeling, simulation, and analysis to complement or to support physical testing, also to partly replace it or reduce it, but not to fully replace it. So we always need physical testing and virtual testing. And with this hybrid approach of virtual testing and physical testing, we can really combine the advantages of representing the product and also the operational environmental conditions on the other side, as shown in this figure from an Airbus colleague here. And then we can combine this and reduce or have more, let's say, test insight, have a more targeted test program, and reduce in the end time, cost, and risk, for example, for critical tests or expensive rigs. For example, if we have 100 physical tests, we could reduce it to only 10 physical tests and simulate the other 90. Or instead of building huge, expensive rigs for only one major component, the trend goes also towards, let's say, smaller, modular, scalable rigs, also combined with virtual testing and simulation. Then the bigger picture again, and the bigger advantage is really if we front load the virtual testing into the design phase and make adaptations, we can really shorten the whole product development cycle, and in the end bring more fuel-efficient aircraft to market in less time. So this is also an impact not only for the manufacturer, but then for airline operations, climate, and so on. And the challenges of virtual testing, we have to say it's not new, of course. It's already accepted by the EASA in the CS25 as AMC, for example, in structural analysis like static strength, bird strike, crash or impact analysis. But the question is, if there's so much more potential, why do we not use it more or everywhere? First, simulation is also not for free, so it costs resources, people to do it. And second, if we want to introduce simulation as an AMC in certification, the question is always how to believe in the simulation results and also how to trust the underlying software codes and methods and tools. So here, our colleague, well, the EASA colleague Wim Doland, really stated nicely the requirements from the EASA side in the certification memo and called it Credibility Assurance Framework for Virtual Certification of Modeling and Simulation. And you can see here the elements like verification of code and solutions, validation, also extrapolation, scalability, and also errors, uncertainty quantification, but also elements like governance and the experience of staff and organization. Also, we need standardized new procedures and cooperation, as we heard today before. And here we have nice activities of international working groups, also with industry like Airbus, Boeing, other companies, and also research organizations like ours and the authorities, FAA and EASA, producing new guidelines, documents to push this forward. Yeah, so in the end, it can mean to do all this, it can even in short term bring more effort, but on the long-term view, we really believe that this can yield the benefits that I showed before. So now coming from the generic view on DLR-specific examples, so again, we have our hybrid or even triangular view of virtual physical testing up to flight test. Then in this building block approach, we see a testing pyramid, here for the structures testing, for example, so from material coupon up to assembly flight test level, and with a trend from more virtual testing on the right side and less physical testing on the left side. Of course, it's only an example, so how much virtual testing is beneficial always depends on the specific test case. But what is important, really to transfer between the different disciplines and components, we think, because the CAF credibility framework that we showed before holds actually for all of them, and we can transfer and learn. For example, DLR example, structural testing for crack propagation tests, virtual physical. We also make systems testing here for movable components, for high aspect ratio wings, ailerons, now building up this test rig in Bremen, flight control system down to actuators. Then also in flight physics, we have to combine wind tunnel testing, simulations, CFD simulations, and flight testing. Here an example of Uran's DDES CFD computations for the NASA CRM model. And then up to flight testing, real and virtual. This we are doing with our flight test fleet in DLR. And again, the cooperation. Here you see a photo some years ago here in Cologne between EASA and DLR in the frame of our bilateral cooperation agreement. So actually now I want to give 3 examples from DLR side. That means covering actually the whole vertical and horizontal level. That means first, flight testing, virtual physical flight testing with our test fleet. Second, a test pyramid for one example component like a hydrogen tank. And third, then the end-to-end chain for a movable component. So first example, the iStar. Our DLR iStar is the newest member of our test fleet. Actually, it's a Falcon 2000 LX. We bought it some years ago from Dassault Aviation. And recently, in the High Fly project with our Braunschweig and Göttingen colleagues, we did some nice flight tests and compared with simulations and computations. And of course, before that, so in the recent months and years, we heavily equipped this aircraft with instrumentation. So IPCT cameras, but also, for example, pressure measurement belts, based on MEMS technique to measure the pressure over and under the wing, only to give some examples. And with this equipped aircraft, we go into flight testing, only to give some examples. Here you can see the pilot in the cockpit making a bank-to-bank maneuver. I hope the video will start. It's quite large, so it takes a while. Yeah, you see the pilot initiating the bank-to-bank maneuver, deploying the ailerons, left, right, left, and here you see the simulation, fully coupled with an aerodynamics, structural dynamics, and 6 degrees of freedom flight dynamics. And also we vary then parameters to see, for example, the influence of rigid or elastic aircraft. Also on the wing you see the pressure distribution here nicely. And then second maneuver, this is now a pull-up, push-down maneuver at transonic speed. So again, the pilot in the cockpit initiates the maneuver, pulling and pushing up and down. And then you can see the simulation again. And then we really compare now the pressure distribution on the wing with CFD computation. And you remember the MEMS pressure belts. And at transonic speeds, it's not so simple. So you can see quite a good agreement, which is good because also the sensor technique is quite new and in-house developed. And also for the flight mechanics parameters, we see good agreement. And concerning the uncertainties and the tolerances that I mentioned before, we introduced here some bands that are also used to create or build, let's say, real flight simulators from our testing colleagues in Braunschweig. And you can also see that it's quite a good match in between that tolerances. Yeah, so the message is here, we are doing that with a lot of flight tests. There are other tests done with the EASA, like ground vibration tests, engine tests, and so on. And here we can learn a lot and also discuss with, of course, Dassault and other industry partners and the EASA to give maybe recommendations if we can believe these simulation methods and also transfer to other aircraft. So second example, hydrogen tank. So I don't want to go, let's say, in all to the details of hydrogen-powered aircraft, but we know it's really new in aviation, and we have not so much or not at all experience and knowledge there. On the one hand, we can learn a bit from our space colleagues, for example, from Ariane, also in Bremen from our DLR space colleagues that much experience in hydrogen handling. But, of course, in aviation, we have much more challenging requirements in terms of these thousands load cycles, load cases, hydrogen handling, tank integration, and so on. So it's challenging also in terms of certification. It's a completely new component. So we need intense physical and virtual testing. So in DLR, we also set up a new testing pyramid in the last, let's say, years now. This is focusing now on the structural testing, to give some example. Again, with a building block approach. And you can see 3 elements. So bottom left, first material screening in gray. And then we go up to liquid nitrogen testing first, before we come, let's say, the more dangerous part, the liquid hydrogen testing. And again, to give some examples, first on the coupon level, for example, we analyze the material first in terms of permeability, permeation of the hydrogen through the walls. We do it both for metal tanks as well as CFRP tanks. And here an example of crack propagation or cracks, let's say, in the CFRP laminates of a CFRP tank. And then also we're building up bigger test infrastructure up to subcomponent and component level, like half tank and full tank test of different sizes, like 400 millimeters, and here the 1.7 meter tank test, also for burst pressure tests and permeation tests, for example. Then the oval aircraft level, again, simulation is really, really important if we want to integrate the tank into the aircraft, for example, the rear fuselage, and want to simulate with respect to crashworthiness. We really need simulation because here we cannot test so often, let's say. And here we also derive new recommendations from all these simulations that we exchange also with EASA, for example. Our colleagues from DLR in Stuttgart are doing that. And then finally, after the structural testing, we of course also need the systems testing. Here an example of our space colleagues in Bremen with a hexapod with an Ariane tank on it, and the hexapod can simulate the dynamic behavior of the tank with the fluid inside. That means in terms of sloshing, for example. And then we also have to simulate, let's say, the filling and the draining of the tank, including the sloshing. And also then again with CFD computation, we can simulate the sloshing, which is quite complex compared to kerosene because we have the gaseous and the liquid state. And this is really, let's say, complex in the behavior. Also then concerning the feeding through the pumps up to the engine, let's say, and this interaction of sloshing, choking, and so on. Yeah. So this is only to give you some examples. And we hope, or we see, we need physical testing, but if we directly put simulations, we also have a virtual testing pyramid, then simulation can really help to spare in the end or make more specific physical testing, validate in between, like here, and then really, we don't know when the LH2 aircraft will come, but maybe it helps to get it a bit more quicker into the market. And then the last example, you remember the end-to-end chain to really shorten the development cycle up to certification. Here we worked in our virtual product house in the ECOMAR Technology Center in Bremen. This is actually an integration platform from the DLR with different DLR institutes. but also industry partners like Airbus sitting in the same building, Liebherr and other companies, and also the EASA is here, let's say, closely involved on technical, but also on management level for this initiative. And Virtual Product House is also focusing then really on virtual certification and end-to-end development for specific components like LH2 tanks, and the main component was a movable of an aircraft wing. So what did we do again? We start with an aircraft, simulate and design the whole wing, including all of aerodynamics, structural interactions, the systems design of the flaps, the kinematics of the flap mechanism, like track rear link mechanisms, for example. Then we focused on a specific outboard flap movable and designed a new component, which is a composite multispar flap, so CFRP component with integral load introduction. And we manufactured it. That means we simulate the manufacturing process first to have both the design and the manufacturing. And then after the simulation, we also went into physical manufacturing. You can see the video in the background. That means the CFRP type of flap we really manufactured to validate the virtual manufacturing. So including all the fiber placement, sensor integration, preforming of the skins and the spars, and then it goes into the autoclave, including infusion and then demouling. And at the end, you have the manufactured flap. And with our flap as designed and the flap as built, we go into testing procedures. Again, for example, structural testing for impact simulation and damage tolerance. Again, virtual testing, physical testing to compare, to learn, to validate. And for example, also systems testing. The systems testing means, for example, if we have a failure in the transmission system, like a shaft rupture or a shaft failure, you can see then the movement of the flap in a co-simulation or multi-body simulation, and then the interaction of systems and structural behavior. And we can also feed it back to the flight performance. And also here, as shown before, we are building now up a physical test rig just in the next months, and then in the next years testing there together with Airbus in Bremen, but also with Liebherr, for example, for actuator components that are used then for the flight control system to, for example, use movables for flutter suppression on high aspect ratio wings. And you can see here the paragraphs from the CS25. So actually here we really produce documents on how to build the model, how to verify, validate, and exchange with EASA on the different paragraphs for systems, testing and manufacturing, to learn from EASA and vice versa. And as we said, now in LUFO and clean aviation projects, together with partners, we're focusing on the high aspect ratio wing, really applying these movables and also this end-to-end chain, and try to mature it as much as possible for future aircraft configurations. So, last slide of my presentation. To conclude, of course, I said I only showed, let's say, few or 3 examples of DLR. Of course, we also have other examples in the virtual engine sector. We have the site, the Crash and Impact Testing Center close to Stuttgart, and also other EASA relevant topics, for example, for UAS in Kochstedt. But to conclude on this presentation, we can say, virtual testing is not new. It already exists as MOC in the CS25, and it has been already increasingly used in recent aircraft development programs, more and more, but there's still broad and high potential, including the shortening of the development time and to spare physical tests, especially for new components. But we have the industrial requirements and also the EASA requirements for concerning credibility framework. So what is the message? I think we heard it a lot today. We have to go for cooperation, learn from others, so we have to learn from the EASA, but I think also the EASA can learn what is possible, and we have to discuss it trilaterally between industry, research authorities, remind again the international working groups to write down procedures, standards, and so on. And then, of course, mature the simulation capabilities at the borders of the envelope and beyond, learn from the different disciplines and components, and further elaborate on specific use cases, maybe, as I've shown before, and really to explode the fully CBA potential then for next aircraft programs, if it's ready, and to use all the benefits that I showed before for digitalization in aviation, for climate-compatible aviation. So this as an overview of our activities. Thanks again for your attention. And I'm looking forward to the other presenters and also for discussions later and questions.
So thank you very much, Christophe, for this very interesting presentation, and in particular the links between simulation and testing. So you can ask your questions already now in Slido. We'll pile them up, and after Philippe's presentation, we'll review all the questions on the first two presentations. So now I invite Philippe to talk about cybersecurity.
Okay, hello everyone. I'm Philippe Leclerc, Product Security Officer of the Avionics Global Services in Thales. This business line is in charge of supporting airlines. We are supporting more than 300 airlines for Thales products. And we operate, repair, we offer online services for customers. And in this business line, I'm in charge of introducing cyber. So security in all we develop, in all our operation, and in all our online services we develop for the customers. So I know Partailles a little, yes. So I will talk to you about cybersecurity and data integrity in aviation. So what we are seeing today is that airlines want to operate more and more the aircraft. Consequently, we see that aircraft is more and more connected to the ground, to IOC, ATC, connected to, and a lot of data are carried through NSP providers. So, in the safety point of view, this environment were supposed to be trusted, which means that some data were not authenticated and nor secured. So now, as the cyber threats are raising due to this augmentation of connectivity of aircraft, we cannot longer trust the environment. So we are not only speaking of safety, but we are speaking about security, which means that the environment is not trust. We have to consider that we face some attackers that will try to attack our systems. You know, security deals with a malicious event that will impact our systems in terms of integrity and availability and confidentiality. And may impact system and people, of course, but not only, as you know, it will impact also company reputation, finance, and international relation. So this slide to explain that we have to consider end-to-end security on all the data that are exchanged in the aviation world. So speaking on the aircraft, up to now we have taken care about the aircraft. We have a lot of regulatory environment that regulates security in aircraft. Some ED standards give the framework that makes the links between security and airworthiness, ED standards. And there are some working group at the EuroCAE level, working group 72, that is currently working at the data security to issue new standards in next year, I think. So this standard will cover data security about data loading in aircraft, but we'll see that is not enough for us. We are speaking about the aircraft. Now we will speak about the environment of the aircraft. To secure the environment of the aircraft is the purpose of Partailles regulation. Partailles deal with all the life cycle of the aircraft, from design to operation, through production, of course. And Partailles is a good example of continuity between security and safety. So we talk about aircraft, we talk about the environment of aircraft, but it is not enough because, as you know, the environment is no longer trust. We face a lot of attackers that try to attack our system, and the best way to attack is to attack through the data that are exchanged between aircraft and ground and between aircraft. Okay, so once we have said that, what can we do to improve our cyber resilience in terms of data? Basically, we do cyber in design phase through ED standards, but for sure we have to extend the cyber introduction and, until the operation phase, which means that any events that is observed in the operation shall be taken into account in the design phase. We have to react more quickly to cyber events, discovered or published on the internet or other, and to be able to introduce correction fix in design phase. Of course, if we think about acting on an aircraft, we may be slowed down by the certification life cycle, the time of the life cycle of the certification. So we have to consider also to securize outside the aircraft, which means to securize the data, the upstream data exchange in terms of authentication and confidentiality and integrity of the data. And of course, we have to permanently monitor the cyber threats that are existing in the aviation world by what is published on YouTube, on internet, on the dark web, etc., etc. And of course, we have to make appropriate recovery and response for these vulnerabilities. A little example now. Some years ago, an Iranian team has published on YouTube a vulnerability discovered on database loading on avionics systems. You can go to YouTube if you want, if you don't know this case, but what we can do about this, we can say about this, following this vulnerability publication, there was not really impact in terms of modification of the design of the avionics systems, which means that we are not reactive at this time for such publication. And this issue is not only about database specific problem, it's more common to any data loading security that is considered in an aircraft. And all this issue may impact data integrity and availability in aircraft. So in conclusion of this slide, we have to be more reactive to any publication and vulnerabilities, which means that we have to act on the aircraft by itself, if it's not possible to act outside the aircraft. For this example, the implementation of security measures in PMAT was able to fix this issue. But again, we have to accelerate the way we handle fix in our system related to vulnerabilities. 2 slides about the difference between safety and security for the probability of failures. If we consider a safety point of view of a system C composed of 2 independent systems A and B, you know that the probability, as there is no common mode of failure, the global probability of failure is rather the multiplication of the both probability A and B. As I said before, in a safety view, the environment is considered as trust. We have the environment is stable and trust, which means that the probability of failure of this system is stable in the time. Even if we have an incident impacting A of B, okay, we have mitigation measure, security measure, but in the time, the safety of the system remains rather the same. If we consider the same system on a security point of view, first, we cannot talk about probability of failure because we are not able to compute probability in cyber. We are only able to compute likelihood of failure. In such cases, the difference is that the environment is not trust. It's considered as malicious and it's composed of attackers that wants to attack our system. If we consider an attacker that wants to attack such system, he will not attack only A, but he will attack A and B to reach common mode of failure. So if we have a failure in such system, it means that the probability of failure and the security of your system will collapse after a vulnerability is found on your system, because as the environment is not safe, this vulnerability will continuously be exploited by other attackers. So what you see in the graph on the upper corner, your global security of your system collapses after. What does it mean? It means again that you have to continuously monitor your cyber threats that may impact your systems. So what can we do now? First challenge is that, as you know, cyber threats are evaluated all over the time. There are new cyber threats, new attacker, etc., etc. And the challenge we have is to synchronize the protection of the system with the rhythm of the vulnerabilities that are found. To do that, we have to permanently monitor incident and event, as I said before. We have to deploy a policy to quick patching our systems. Again, if we face if we are acting on an aircraft, maybe the fix will take some time due to the certification. So you have to interact outside the aircraft by securing the data outside the aircraft. Okay. So this is a conclusion slide. As I said before, we have to consider end-to-end security for aviation data. We have to make some reflection about the certification process to handle cyber threats and how to fix cyber threats in the frame of the certification process today. We have to prepare the cyber resilience in operation, which means that we have to filter and to securize all data during the operation outside of the aircraft. And as these threats are not specific to aviation, we have other industries facing cyber threats in terms of data leak, data attack. There is a good opportunity to exchange with other sectors who face same challenge and same threats from a cyber attacker in terms of data integrity and data authentication. We think about nuclear industry, automotive industry, for example. That's all for my presentation. Thank you for your attention.
Thank you, Philippe. So I think we have a number of questions for the first two panelists, which will be shown in a minute. So the first one is not for the panelists. Maybe, I don't know if Marcella or Colleen want to take the first one.
Okay, yes, good afternoon, everyone. Yeah, the CM is still under work. I can't promise exactly when it will be issued, but it's more about us being able to focus the right amount of resource on this topic, and we look at trying moving that forward in the coming months. But I can't give you an actual date when we will issue this memo. Sorry.
Thanks, Colleen. So the second question, I guess, is for Christophe, but maybe as a supplier or in support of some manufacturers, do you have any indication on the question about the percentage of tests which could be reduced?
I mean, I think it's, as we had before, I think it's difficult to give a specific number. I mean, we are not certifying by ourselves or make products because we have a research organization, though we also have a design organization to modify our aircraft for flight tests, so we don't have direct numbers. We rather try to, as I showed, for example, for the hydrogen tank pyramid, go always for physical and virtual testing and really see where it's worth to simulate and where not, because sometimes the simple physical test is just the best one and we don't have to simulate. But sometimes it really helps, as I showed for the crash simulation, for example, impact simulation and so on. So we always try to learn, do both, try to compare, and I think then we can really go to high numbers. Sometimes we can really completely replace physical testing. As I gave the example before, if there's, and that's also information, let's say, an objective from industry, if there are, for example, 100 tests and you really have good simulation methods, maybe you can really go down to 10 or 20 tests and simulate the other 80 and use the physical test for benchmarking, for validation, and really have a targeted test program. But from the simulation and the combination of virtual and physical testing, you can really learn and make more specific test programs. And that's the idea. And this can really vary from, you don't have to do it, use physical testing, up to 100%. So it really depends on the components, on the case.
Thanks, Christophe. I think that answers partially the next question as well. I don't know if you want to add anything on the next question, which is more directed to your presentation. Or I don't know if, Colin, you want to add something on the EASA LOI?
I think, so on simulation, really it depends on a case by case, and it's really about validating the model for the cases you're doing. We have to have confidence in your model in order to do that. So there's always a certain amount of mention today. We always need a certain amount of physical testing to do to validate that model. But in terms of this, in terms of critical flight conditions, yes, we can do that. I mean, I think, for example, in eVTOL, there are a number of critical conditions, for example, on eVTOL aircraft, which are very difficult to flight test. And so for in these cases, we are more likely to rely on simulation. But the most critical factor is validating the model first, and then we can take from that what the scope and what it can be used for.
Thanks, Colin. So I think the next question is also for you, Christophe.
Yeah. So have you certified any project with regulators? So on the one hand, as I said, we have internal design organization in Braunschweig for our flight test fleet. So if we make changes there, we have to certify it, of course, with EASA or the Luftfahrtbundesamt. And mostly it's also physical, but there also we use sometimes simulation to improve that process. This was done, for example, for pods under the wings, or also for ice protection systems and so on. Because every instrument that we are putting on the aircraft, because I showed before the heavily instrumented Dassault aircraft, has to also be certified, or we have to get some permission to flight there. And there we want to use more and more simulation. That's why we make this iStar like a technology platform for virtual certification. And for the other cases that I showed, it's rather, I mean, there we are not certifying it. We are not certifying, for example, the movable or the tank by ourselves. So this is then what, for example, the manufacturer or the applicant is doing. And of course, they should do it on ourselves. We are only, let's say, the research organization, but I think it's important to go into trilateral discussions, what is possible, and the industry knows what they want to do, and that's their business, let's say. But I think if we learn trilaterally, we can go forward there.
Yeah, I think it should be clarified that DLR is a research institute, it's not an aircraft manufacturer. You are a research...
we are a research organization, yes. And we know that certification is always a very sensitive topic, and we discussed that also some years ago with the EASA and Airbus, that we are not saying what has to be certified, for example, and we are not speaking for Airbus, but we are in really close contact sometimes also on the research area where we can help, for example. And there I think this, let's say, trilateral discussion is good. And also with the EASA, we have this memorandum of cooperation to discuss, let's say, the potentials or where AMCs, for example, can be changed or adapted to include modeling and simulation, as it was proposed, for example, in the CM.
Thank you. So the next question is for you, Philippe, about COTS. So I let you answer the question.
Yes, it's true that we integrate a lot of COTS software modules. That's true in not in avionics, but in other services or systems. How do we manage vulnerabilities found in COTS? First, we use dedicated tools that are able to scan what is integrated in our systems and is aware of all the vulnerabilities found up to date. So once we detect vulnerabilities, we are able to identify in which COTS the vulnerability is found and request an action plan to fix these vulnerabilities. But proactively, of course, it's quite difficult because there are always vulnerabilities found every day on every piece of software. So we have to introduce a real vulnerability management policy inside our organization to cover that. That's all I can say.
Thank you. So the next question, I don't know, Anna Maria, it's a bit specific. Can you take that one? So Anna Maria is a colleague from the POA section. If the mic can be given to her. It's about the credit for digital manufacturing for physical process.
Thank you. Yeah. Well, this is a bit novel to me, but what I can say, if a production organization could demonstrate that they have the control over the process, and they can ensure that that they're conforming to design data by approved design organization, I believe we could take credit. Now to tell to which extent, this is a bit hard because it would probably depend on case-by-case basis, and this would have to be decided by between the POA team leaders and the organizations themselves. But for sure, if design data is followed and the organization has control over the process and can produce a product that will be for safe operation, I don't see why not.
Thank you, Anna Maria. So the next question is very specific. I don't know whether Charles or Colin have an idea.
Okay, so this one, I mean, it says in the policy that the FAA will issue a special condition, and then we would naturally review the special condition, but our expert has said what they've written seems to make general sense, but in fact it's never been used as an alternative means of compliance to date, so.
Okay, thank you, Colin. So another question on cyber for you, Philippe, and for EASA. I'm wondering who can take that one. Rachel, do you think? It's a very I don't know, Philippe, if you have the answer to. I think we have experts in the room on cyber and GNSS. I'm looking at the colleagues. Maybe we'll take that question with us, and we can come back to the author later on. So a lot of questions are addressed to EASA. So I will first look at the panelists to see whether they can answer, and if not, I will look at the colleagues. Standalone cyber changes on ICA. Wow, that's another very specific one. Looking at the colleagues, I don't see any volunteer to take that question. So Federico, if you bear with us, that question is too specific. We need to talk with the ICA experts. And the next question is maybe for you, Colin. Whether we have...
So within EASA, we've set up a network of modeling and simulation experts that are working across different areas so that they can support one another. We're developing in their training, and so we're investing in it. We don't have such a dedicated resource. We are using resources that are already working in those areas, but more particular, taking a leaning towards the modeling and simulation areas. So.
Thank you, Colin. So if we have no more questions, maybe we'll move to the next presentation. Okay. Francesca, the floor is yours.
Thank you. My name is Francesca Barosio, and I'm the initial airworthiness manager at Leonardo Helicopters. With this presentation, I would like to briefly present the different maintenance approaches. Then we will deep look at the condition-based maintenance and the reason why and how we can consider this condition-based maintenance an alternative to the traditional approaches. Before to start, I would like to do some definitions. We can identify two main different philosophy in terms of maintenance. The first one is the reactive maintenance, where the maintenance activities is performed after the occurrence of a failure. And the second one is the proactive maintenance, which is performed before the occurrence of the failure. Within the proactive maintenance philosophy, we can identify some different maintenance approaches, which are the preventive schedule maintenance, where the maintenance activities are performed at a schedule interval. And then we have the condition-based maintenance and the predictive maintenance that use sensor and data to provide the evidence that we need a maintenance action, to perform a maintenance action. Looking at a typical maintenance program for Leonardo Helicopters, for example, we have a different input coming from, for example, analysis and tests performed during the certification phases, like as analysis performed in to provide compliance to 29.1309 or 29.571, for example, for fatigue. And then we have also the scheduled maintenance task derived from the MRB process, so linked to the MS3 analysis, together with the possibility to introduce some unscheduled maintenance task based on in-service experience. Moving on to the condition-based maintenance, I try to summarize here some pro between the conventional, let me say, preventive maintenance and the condition-based maintenance. If we look at the preventive maintenance, for sure, it is based on well-noted and consolidated approaches, as we have seen before. But moving on to the condition-based maintenance, we can assume that there is the possibility to improve the maintenance cost, for example, improving reducing the downtime, increase the aircraft availability, optimizing the operability of the aircraft, and also there is a possibility to have a reduction of unscheduled maintenance. All those indicated benefits, let me say, are linked to the fact that we can take credit for the models that drive the condition-based maintenance, and we also have a full coverage of the failure mode that require the maintenance action, together with the fact that we can have a sort of data aggregation so that we can organize the stop of the aircraft based on the opportunity linked to the operability and the environment of the aircraft. Moving on to the detail, I identified 4 main steps for the condition-based maintenance, and we will go into detail in the next slide. About the data acquisition, it is important to, for sure, acquire a current number of parameters to properly monitor the system. Then we have also the need to select the data and the position of the sensor in order to collect reliable data to be used for collective condition-based maintenance. Finally, it is also important that the data transfer chain from onboard to ground station where the data are processed should have an adequate, a certain level of robustness and integrity. The acquired data are then processed in order to enhance the visibility of alteration with respect to a reference model. A combination of different processing techniques can be used depending on the type and amount of failure mode that need to be monitored. In particular, they could be model-based algorithms, which are basic on the physical knowledge of the system behavior, but also database algorithms, which are based on data-driven techniques, like, for example, in the last year, the machine learning and deep learning techniques, which are gaining visibility thanks to the fact that the digitalization allow to have the availability of a large amount of data in this year. Then we will go to the data monitoring phase. So the processed data are monitored with reference to a threshold defined within a model algorithm in order to inform the operator that a maintenance action is needed because there is the risk for a failure condition. Conventional processes involve the use of models which are based on the fact that each parameter is compared to its specific threshold. But in the last year, we can also take credit or take advantages considering multivariate models, which are associated to machine learning techniques, for example, where the multiple parameters are fused into a single indicator to be compared with a threshold in order to detect that a maintenance action is needed. The goal of the condition-based maintenance is the fact that we can perform maintenance only when the maintenance is required, and it is needed because there is the risk of an impending failure. Instead, to do this at prefixed interval, sometimes determined well before the occurrence of a failure. Then, to summarize the step that I have identified here, which is a step forward from the preventive maintenance approach, which is the typical one, to the condition-based maintenance, is based on different steps. And the first is for sure the capability of acquiring the current number of parameters, which allow to detect all the failure for which we need a maintenance action. About this, together with the physical sensor, which are limited in terms of possibility to install it on the helicopters, for example. Thanks to the digitalization and the machine learning techniques, today we are able to acquire and process a large amount of data from, for example, experimental flight data and also customer flight aircraft usage, which can be used to implement virtual sensors. Those virtual sensors can be used to reconstruct a signal from components that don't have a physical sensor associated, and then we can get a complete view of the behavior of that component. The second point is about the definition of the requirements for the data module according to the criticality of their intended use. About this, I think that an important point is the fact that recently the working group related to rulemaking task 711 has been closed to define the AMC and the guidance materials applicable for a vibrational monitoring system, which can be developed for credit. So those AMC and guidance material will define the requirement for those systems to provide a system compliant to 29.14.65 requirement for full credit about this system. And I think that it could be useful to understand if the same work can be used and translate, for example, to address it also not only for system based on accelerometers, but also for system based on model data driven techniques, like, for example, the system that can drive the condition based maintenance. At the end, there is another point related to the fact that we need to define a process to validate this kind of models. So to conclude, I think that today the method for predictive maintenance are typically considered without credit. So the maintenance raised by those kind of systems are performed in addition to the standard preventive schedule maintenance programs. Therefore, a step forward with respect to those well-consolidated approach is needed. What I think is that instead to have a complete removal of a prediction of a schedule maintenance program, what is more feasible could be to have a sort of hybrid maintenance program where some preventive maintenance tasks are completely replaced by the predictive task. So this could be a more achievable goal based on the failure mode identification and the coverage that we can assure through model-based techniques. Nevertheless, even in this case, we need to have certification rules and guidance material to define how to give credit to this model. That's it. Thank you.
Thank you, Francesca. That's a very interesting example of very concrete implication of big data collection and computing. And I see also some synergy with the previous presentations, both in terms of data modeling and also in terms of data integrity. So it puts everything together nicely. So I'm looking forward to the questions. But before we go there, it's my pleasure to invite Mr. Yao to talk about end-to-end digital processes in COMAC.
Okay, thanks, Gregory. Ladies and gentlemen, good afternoon. I'm Yao Xun from COMAC. You can call me Yao. Well, I'm specialized in aircraft architecture design and system integration. This is the first time in Cologne. It's my pleasure to share our experience and practice regarding on the MBSE, that is the model-based design. Okay, sorry. My presentation consists of 4 parts. Firstly, I will quickly review the background of the MBSE, the coming with COMAC planning of the MBSE. Then I will introduce the practice in little bit of details, and then summarize with what the challenge we have. Both we know that for civil aircraft, they have plenty of the complex systems. For each manufacturer, we will face the numerous difficulties and design issues, such as the challenge of capturing requirements, which is easy to ignore, and the complexities of logic, the design logic, which is hard to express and can lead to ambiguity. Also, we have the huge amount of the interfaces, which is hard to identify the defects. Okay, INCOS also post a roadmap for the MBSE. In this diagram, we can see the vertical axis. I think we believe that it is an inevitable trend to transform from the document-based design to model-based design. Okay, Airbus and Boeing are the pioneers of the civil aircraft OEM. They are also applied for the MBSE in their product development. The results is positive in reducing the development cycle and the design issues. Also, the results is useful for us to promote the MBSE for our product development. Okay, COMAC has successfully developed the C909 and the C919. There are more expectations and requirements for the next generation aircraft development. So we make a plan for COMAC MBSE practice exploration. Okay, this is the typical V model in the civil aircraft. On the left side of the V, based on the traditional document-based design, the information on the documents is systematically incorporated into the models by constructing scenario model, function model, architecture model, and the ticket mockup. On the right side of the V, we carry out simulation verification based on the models. The verification is continuously pushed to left to ensure the design fully meets the requirements. Okay, we carry out the innovative practice by advanced methods driven by requirements, fully implement MBSE to promote civil aircraft development with high quality and efficiencies. By By modeling, we can capture requirements, define solutions, and also optimize and verify design. Doing the modeling in the scenario models, we can take the aircraft as a black box. The key is to sort out the real feedback of the aircraft and the different operating scenarios and different fault conditions. Requirements are captured through the function models. Then the aircraft is turned into the right box. For each function, analysis is conducted to obtain the function requirements and interfaces. Also, we can check the interface match by using tools in the architecture model. The design is verified by the mechanics model. Under the scenario models, we carry out simulation verification to ensure the system logic correctness and integrity. Okay, to ensure the continuity of the data, the architecture models defines the simulation model architecture, interfaces, and the scenario models, and specify the scenario cases. Through standard interface conversions, this information is transferred into the simulation model to ensure the occurrence of the data. Also, we have also planned the digital mockup that cover the entire product life cycle, expanding the digital mockup from the design fields to the manufacture and flight test and custom service fields. By reorganizing and refining the different views on the same model, we have established a connection between the front end and the back end data. We have also built the online design environment, helped by Dazzle, which can put all the architecture design, structure design in the same environment and build the process. So next, I will introduce some practice cases. During the modeling, we conduct model-based scenario analysis to capture design requirements. By analyzing the scenario timing and logic, we obtain aircraft response as text. We conduct a model-based function analysis, combined with the operational scenarios, analyzes the logic of a functional operation, identify interaction relationship, and capture functional requirements and interfaces. Based on the function analysis results, we carry out a model-based architecture design, define interfaces, and get a unified architecture for simulation. For the design architecture, we further conduct model-based mechanism and analysis to analyze the working modes. We identified and expected errors in logic, verify interface matching, and improve the correctness of the requirements and interfaces. Okay, based on the architecture and the interfaces, we can conduct the model-based safety analysis to analyze fault failure propagation logic, carry out a fault tree integration. We integrated all the system fault tree on the aircraft level, and to support the aircraft safety assessment. After the design work finished, we will use simulation methods for design, verification, and validation. For example, the aircraft power system integrated simulation. We built simulation models of primary energy system, secondary energy system, and power consumption loads to complete the model integration. Completed the aircraft energy requirements and the interfaces validation using the integrated simulation. Based on this work, we have achieved the electrical, hydraulic, and pneumatic requirements calculation for different scenarios, also as well as the consumption rate of the fuel profile. we have achieved the construction of the fully three-dimensional real-time online and single data source digital mockup. Based on the TC and main skeleton model, carry out the space allocation mockup, as well as the installation interface control model and the particular risk analysis model. And continuously iterative. Now it's time for the summary. Based on the previous exploration, we have achieved that. First, that we establish a forward design process for civil aircraft based on requirements, and throughout the design for scenario, function, architecture, mechanism, safety, and simulation. The second is that we form a complete design chain from aircraft level, system level to atom level, ensuring the upstream and downstream data transmission and traceability. We also customized deeply tools based on the design process and the development requirements, achieve partial business automation, and improve design efficiency. Finally, we've constructed a model management system and process, coordinate and standardize the various major design simulation activities, and ensure the unified management of the model data throughout the entire life cycle. Okay, for the future, we also face the many challenges. How to make designers change their conventional design approach, accept model-based design process, and learn new tools. Sometimes someone, the engineer will ask us, my document is very excellent and approved. Why need we to build new models? So at the project level, also we need to accepting the associated costs. The second that is the data source. The implementation of MBSE required to ensure a single data source for all models and data, ensuring the traceability of design data. But the barriers between different software tools lead to some uncertainty. The third one is that how to evaluate the validation and the efficiency of model data as a product of design and obtain recognition from the authorities like EASA, which raise more demands on the mode. Okay, that is all for my presentation today. Thanks for your attention. Thanks. Since the limited time, I would like questions through email. This is my email address. Yeah? Thanks all.
Thanks, Mr. Yao. So before we go to the Q&As on the two last sessions, I have a question for the panel. Now that we've heard different perspectives on the digital mutation of the sector, how far do you think we have gone? So do you think that the biggest wave of transformation of digitalization for aviation is behind us or in front of us? I know who wants to start. Maybe Christophe?
Yeah, quite generic question. I mean, I showed it a bit in my presentation. I think both. That means at the moment we have really specific, let's say, projects, internal projects, also German-funded or European projects. For example, in the Clean Aviation project, EASA is also involved there on certification, virtual certification. So there we are going on specific components, trying to show up specific solutions. But as I showed at the beginning in my presentation, this really virtual certification or having a virtual flight test or really reducing a big amount of physical testing is really, let's say, far beyond and a long way to go. But still, it's, let's say, a vision and a long-term goal, and I think it's worse. And also all the other topics that the colleagues showed, but I think they can comment better. We have specific activities also at DLR on AI, on prescriptive maintenance and so on, but we have to bring it also into application and really use it that it's a specific benefit, because sometimes the digitalization is only a buzzword or generic, but it's important really to apply it that it brings you benefit and not do it for, let's say, a purpose. And we as a research organization, yeah, by definition, we can only go to TRL 6, so to say. But more and more we come into that level together with industry that we have to push it beyond so that really it comes into a product.
Yeah, so still a lot of promises, but yet to come. Would you agree, Francesca?
Yes, in part is this the point. We, as company, for example, we are working on it, and now I think that it is the time to have also EASA on board to understand how to give a real credit for what we are doing, for what we are working on. So I think that the time is now mature enough to start the discussion more in more detail, also with the authority about this.
And make it happen. I don't know, Mr. Yao or Philippe, do you want to add anything?
On the security aspect, there's a lot of things to do, for sure, in securing the data. So there's a huge work to do, for sure, yes.
Just clarify one thing is that currently the MBSE has not fully applied for our chap development. But past the C909 and the 919, we also use the traditional document-based design models. But in some of the departure fields, we use the digital design methods, like the identification of the aerodynamical parameters, like the digital mockup, and also the digital manufacture in our factory. We believe that the MBSE will bring the benefits and the value for us, for our development. So our goal is that to promote this MBSE in a new type, like the C929. Okay.
So thanks. So I take from your answers that industry is moving fast, there is still a lot to come, and authorities need to synchronize and follow. That will be discussed later in the next session. So maybe if we could go to the questions on the last presentations. So clearly the first question for you. What is your view on the readiness of the regulations for the use of
condition-based maintenance? But I think that we need to work on the regulation, as I said. Maybe, I don't know if it is only a matter of regulation, for sure, guidance material or detailed guidance material with to capture this aspect and the benefit or the improvement for condition-based maintenance in terms of certification, for sure.
Okay. Anna Maria, if you want to add something, you just let me know. So the next question is also for you, I believe, related to your presentation.
As a link the data acquisition, data processing with the certification. Well, they are part of the same, let me say, process. So the process, in my way, starts with the data acquisition and with the maintenance or the data monitoring. So there is a link because we need to acquire data and then to process that data in a correct way. With respect to the certification, this is what I'm looking for. So the point is, what are the requirements that we have to take into account in order to define all the specific requirements for all the parts involved on this, let me say, chain, between from the onboard sensor, but also the virtual sensor, so the onboard data used for the development of virtual sensor, up to the monitoring of those data and the definition of a maintenance. they are linked because we need to understand the requirement and then develop the systems that we have to use, the sensor and so on.
Thank you. There are a few questions on your presentation. I think it triggered a lot of interest. The next one is also related to your presentation.
This is my point. Maybe we can consider the condition-based maintenance, or better, let me say, the model that drive the condition-based maintenance, like as an health monitoring system. But if you look at the vibration health monitoring system, and for example, as I said, to the new guidance material related to the credit for the vibration health monitoring systems, it is also true that this specific group works on the specific system. So they are talking about accelerometers and so on. What we can consider, for example, is the fact that within this working group, they address both the onboard and the ground systems. So I think that there are some commonality, and we can also take credit for the works that have been performed in this rulemaking task, in my view, honestly. But they have to be tailored for another generic monitoring system, which is not based on the accelerometers only.
So there are some synergies possible between the two topics.
Yeah.
So the next question is still for you.
The improvement, as I said, is in terms of maintenance cost, mainly, because you don't have the maintenance cost related, for example, to large downtime, okay, and the fact that you have to do maintenance at the scheduled intervals every time, independently from the fact that you need the maintenance in that moment or not. So this is, in my opinion, the improvement that we can use. And also the fact that if we are able to define a trigger in a way that you can organize the maintenance activity in a way that have low impact in your operability, I think that this is an improvement with respect to the scheduled maintenance.
And the next question is also for you.
How do you think to transfer the condition-based approach?
That's a challenging
in
question. Is there any way the sensors could be adapted?
Yeah. My point is that, okay, probably it's not 100%. It could be to understand a first approach could be to have a sort of hybrid, because I'm sure that some maintenance tasks can be replaced in some cases, but we have to look in detail. But in other case, considering the failure cause or the failure mode that drive the functional failure, I'm not so sure that we can cover everything with an approach style condition-based maintenance. But let's start step by step.
Okay, thank you for that. So I have another question for the panel. What do you think are the biggest challenges and the most important enablers to go faster on the digital mutation? And who wants to start? Philippe, you want to start? Enablers and challenges?
My most important challenges this year is Part IS on my operation, of course. Enablers to make people think about cyber, of course. cyber threats. It's not only in movies, of course. It's real life. So to make them to increase the awareness of people in cyber, it's a most enabler for us.
Who wants to go next? Christophe?
Enablers and challenges. Yeah, so the enablers, I think I showed, so the digitalization yeah, itself, I mean, there's so much more computing power compared to 10 or 20 years ago, so this is increasing more and more, so there's much more potential than we really use or exploit. But the challenges, on the other hand, as I described, is really to bring it into application, into industrial application, and also the topic of certification. And that's, I'm not saying that only because I'm here with the EASA, because it's really the critical point to bring these, let's say, the developments into a product. Look at the hydrogen tank. I mean, even the industry, also the EASA, is really, I can say that, struggling with that, or there are a lot of question marks. And these are the challenges, and then really to transfer from the capabilities that is possible, let's say, from a research perspective, but also then bring it into an industrial product that is still better than the current products. This is a real challenge. And one enabler and challenge, I think, what I said, is the cooperation again. So these international working groups that we have, also the bilateral and trilateral, let's say, working groups and all that, or these conferences here, I think this is really the key. Because, I mean, if we only simulate on our own, it will never help to bring something forward. So sometimes enabler and challenging at the same time.
Yes. Mr. Yao, any thoughts?
Yeah, I think the challenge firstly is the philosophy of data. We need to let the engineer is to realize the value and the benefit of the digital design. And secondly, I think that is the date. How to transform all the traditional document-based information to the date, to the models, to the structure date. I think that, based on this structure date, the huge amount of the data, we can use the AI or the others digital design methods. And the third is that I think the reliability of the listed, the models, and also the credibility of this. That's all.
Thank you. Francesca, any additional thought? It's not easy when you speak last. Any other idea to add on challenges and enablers?
I think that the challenges could be the fact that we have the opportunity to have a lot of data, a lot of information now with the digitalization, with the data lake, etc. But we have to understand how we can use the data and what kind of data are usable. In fact, because I'm not sure that they are 100% usable.
Thank you. So I see we have another question. Interesting question. Christophe, maybe that one is more for you.
I did not focus so much on AI today. Of course, also in DLR and German Aerospace Center, AI, let's say, is everywhere. May it be in robotics, in material recognition, in flight physics, and so on. So here it's more also in physical flying. So also in flight physics, more and more we are using AI methods or machine learning methods. Let's say, but it's important concerning that question that the physics behind that are understood and that they're still in it. Because if you apply surrogate modeling or also AI models, it's good and helpful, but the engineer and the physics should remain and should be in the loop. And then, if you then really apply it, it can be helpful. For example, if you have really concerning flight physics, really large data, and then searching the right points. Also, there we had some nice applications now using AI and machine learning. Than in flight physics. It just accelerates then the huge amount of data. For example, if you consider the real and the virtual flight test that I showed before, I mean, the question goes towards physical flying will decrease it. Yes, of course, but in the analysis and the comparison between simulation and real flight testing, we can again then apply machine learning methods to analyze the data and then again go into virtual physical testing. So this is one answer, but it's a broad field.
The question might also apply to Comac or Leonardo Helicopters. I don't know if you have any projects involving AI.
No, at the moment.
Nothing to add?
This is also what I want to ask.
Oh, there is a question from the floor. Maybe Mohamed, if you can move to the mic, or meet halfway with EASA.
So Gregory, certification by analysis is not new. Means we have used to do certification by analysis with JAA and Airbus for aircraft galleys 35 years ago. Whole galley used to be certified by analysis, all hand calculations. But with the help of the technology now and with the power of computation, in my opinion, will be very helpful basically to do the certification by analysis. But we feel as an industry that regulators are way behind basically in terms of catching the industry to support the certification by analysis because there is no proper guidance available for what to do. We have developed on the SAE side, we have developed as an industry together, we have developed some what's this called guidance materials for recommended practices, but we believe basically that the regulators, either as EASA, FAA, or other regulators, need to come up with something basically which could be helpful for the industry.
Thank you, Mohamed. I don't know, Colin or Rachel, if you have any reaction to that statement. Point taken, and there is work underway. So thanks, Mohamed. The point is taken, and that's something which we are working on, and maybe the message is that we need to speed up a little bit the work on that. On the other hand, I think we have to be careful about what we accept. I think what Christophe gave as example of the work he's doing with Christophe and this model they are developing to assess the reliability of the model is something which goes in the right direction. I don't know, Christophe, if you want to react on your side.
I agree with the colleague that it's important to have the EASA or other certification authorities early in the loop. That's also why we, in our, let's say, bilateral memorandum of cooperation, have exactly this CBA topic also there. And we mentioned the certification memo from the EASA. Okay, it's only still in a draft state, but I think there are really good points of this credibility assurance framework. And it's also then important to transfer to other disciplines, because the international working groups that were mentioned, they are existing, for example, in flight physics. There are then nice roadmaps and guidance documents. There are also working groups in structures, mainly, because in structures it's mainly applied CBA, but it's important to learn from each other that also, let's say, these documents are harmonized so that the flight physics guys are doing similar approaches than the structural guys and so on. And that's what I tried to show also in my presentation.
Thank you. So I think the panelists were very disciplined. We are a bit ahead of schedule, so we can extend a little bit the networking break. I suggest we meet again at 4 o'clock, and in the meanwhile, enjoy the break. Thanks a lot to the panelists.
Thank you.